Do you know what is the antenna violation in VLSI? Do you know what are the various plasma processes that can contribute to the antenna violation in VLSI? Do you know what are the reactive and proactive methods that we can apply to mitigate the antenna violation in VLSI? Let's start our journey to know all the answers. Hey guys, welcome back to the computer screen, and in today's episode we are going to discuss the below points. Vertical cross section of a chip touch basing the FEOL, MEOL and BEOL layers, antenna phenomenon and its infographics. Next, we will cover the semiconductor CMOS process and the various plasma processes that are being used. Next, we will go through our antenna damage action replay and infographics to understand the damaging process. Next, we will cover the physics happening behind the antenna phenomenon, and we will explain a ratio which is called the antenna ratio, closely related to the physics happening behind. Next, we will talk about the present VLSI methods of antenna issue mitigation and some infographics to understand the mitigation methods. That's the menu for today, and without any further delay, let's begin. Vertical cross section of a chip. So here we are using the vertical cross section of a chip. This picture has been taken from Wikipedia. Here I will point out the different layers. First one is the FEOL layer. Here the transistors will reside. Next, there are few other layer components which are very closely spaced with the FEOL, like contacts, etc. Those are called the MEOL layer. And the entire metal routing process through metal and via stack are under the BEOL layers. Now, the reason of keeping this slide is to make an impression in your mind about the different layers, starting from the silicon surface, reaching up to the maximum metal layers. Shortly, you will understand the importance of this slide in upcoming slides. We're done with this particular slide, so let's move on to the next slide. What is antenna effect phenomenon? At present, chemical etching has been completely replaced by hot plasma etching. Plasma-related processes are used for CMOS process flow for etching and deposition. The gaseous plasma contains charged particles inside. This charge gets transferred to the under construction floating metal routes, which may be connected way below up to the gate areas of a MOSFET. At the same time, such metals may not be connected to any diffusion areas in the FEOL zone. Such metal wires act as antennas, that is, charge receptors that pick up electrical charge from the plasma gas. So in this line, you understand the meaning of the word antenna, because here the metal route is acting as an antenna to pick up charge from the plasma environment. Charge accumulation on the metal strip is proportional to its length. That means the larger the metal area or the length is bigger, the more the charge gets accumulated onto it. So here we are done with a short and sweet description of the antenna effect phenomenon. Let us move on to the next slide. Antenna phenomenon infographics. Here we will take the help of our infographics to understand the phenomena during the fabrication process. Here is our silicon substrate. Source, drain. Here is our shallow trench isolation. Gate oxide is grown here. On top of that, poly is grown and connected to the metal one. And after the metal one deposition, we have to etch the metal one as per the mask. So the plasma is coming down from the plasma chamber on top of the metal one for the etching process. And in this gaseous environment, many charge are getting accumulated on the metal one surface. Once this amount of charge is sufficiently high, it causes a breakdown of the gate oxide insulator and the charges pass on the silicon. This infographics helps you to understand the antenna phenomenon happening live during a CMOS process. We're done with this particular slide, so let's move on. What is antenna effect phenomenon? We will go through some more points to dig deeper inside the antenna effect phenomenon. Aforementioned metal wires built up high potential difference on the metal side through the piled up charge. As a consequence, high electric field builds up across the gate oxide of the metal oxide semiconductor, that is MOS structure of a MOSFET. sufficient amount of charge creates a percussion path to the oxide for the drainage of the charge. This percussion path is a small path that is created by high amount of charge, and this is just a beginning. Severe drainage lead to the gate oxide breakdown, consequently damaging the MOSFET. Alternatively, in less severe drainage, non-damaged MOSFETs, hot electron generation, abbreviated as HCI, may take place, causing faster aging related to the performance degradation of the MOSFET. Yes, those MOSFETs which are not getting damaged during the application process due to the antenna phenomenon, even here a percussion path may be existing there where low amount of charge is getting accumulated, and these are causing the hot electrons gathered in the oxide, causing the aging. That means performance degradation of the MOSFET in the long run. We are done with this particular slide. Let's move on to the next slide. Now, in this slide, we will talk about the semiconductor CMOS. It's a brief walkthrough of the CMOS process. So here is a infographics. So first we do the deposition, then we use a photoresistive coating, we use the exposure, developing, etching. I have kept a green highlight here to make it separate from any other steps. Then there will be ion implantation, and then there will be the stripping of the remaining mask. So this is a cyclic process. It keeps on operating for formation of the metal routes in the BUL region I have shown in the first slide. The FUL and MUL obviously go through this process. However, the BUL goes through this cyclic process several times, and the step marked in green, etching, is the process step where we are using the plasma, and here the chances of getting the antennas. Don't think that antenna violation is happening to only metal one. It can happen in any of the metal layers as shown in the picture where I have marked the BUL layers. We're done with this particular slide, so let's move on to the next slide. Different types of plasma process. Now this is going a bit deep in the semiconductor CMOS process. Here we will talk about 3 different plasma process, and that will enhance your knowledge about how the plasma process is done and what is the respective importance, and we will correlate these things to the antenna damage later on. Conductor layer pattern etching process. Here the amount of accumulated charge is proportional to the perimeter length of the conducting metal stripping above. Etching process splits the conductor layer plates into multiple routing patterns. Perimeters of the pleated routing are directly exposed to plasma. Here we have just touched base one particular type of plasma process. Next, etching process. Here the amount of accumulated charge is proportional to the area of the conductor layer patterns. Etching process remove remaining photoresist layers after etching processes of a conductor layer. Area of conductor layer pattern is directly exposed to plasma. Can you spot the difference? In the first one, the perimeter was exposed to plasma. Here the area is exposed to plasma. Next, contact etching process. Here the amount of accumulated charge is proportional to the area of the total area of the contacts. Contact etching process dig holes between 2 conductor layers. That means we have metal 1, metal 2 stack, right? We have to dig a hole through it to make the via, right? So there is particular etching process is used. Here the area of all the contacts on the lower conductor layer pattern is directly exposed to the plasma. Now you are familiar with the 3 different plasma processes that are used in the semiconductor CMOS processing, and in this particular process steps, the plasma affects the metal layers and may create the antenna problem in different ways. We're done with this particular slide. Let's move on to the next slide. Antenna damage action replay. Metal or via stacks are built layer by layer. First, metal 1 is deposited and all unwanted portions are etched away by the plasma etching. Then the metal geometries, when they are exposed to plasma, can collect the charge from it. So at this point, you may recall the 3 different type of plasma exposure that I have just talked about in the last slide. Once metal 1 is completed, via 1 is built, and then metal 2 and so on. So with passing stage, the metal geometries can build up static electricity. If the charge collected is large enough to cause the current to flow to the gate, this can cause the damage to the gate oxide. Long metal lines are prone to such failures, ending into fabrication yield. That means if the antenna damage happens, the chips that are coming out of a batch, huge amount of chips will be defunct. So those chips which has gone through the antenna damage, those will be non-functional. That means we have a higher yield entire fabrication batch. So we are done with this particular slide. Let's move on to the next slide. Action replay infographics. Here is our expectation. Here we'll go through the expectation in a semiconductor process. Ideally, that should happen. Here is our diffusion layer, and here is our gate oxide and poly from a MOSFET. Here we are reaching up to M1, and here also we are reaching up to M1. Then we are reaching up to M2, which is connecting the diffusion zone up to the gate area. So this is a kind of wiring that is inside the circuit, and we expect this thing to happen as shown in the picture through the various process masks in the semiconductor fabrication process. What we have there in the reality, diffusion layer is here. Here is the poly and gate oxide. You can compare the two things. Here we are reaching up to metal 1. Then here the plasma induced charge accumulation happens on metal 1, which may cause the breakdown of the gate oxide. Here is the plasma environment, and here goes the breakdown once all charges which have accumulated exceeds a certain limit. So this is the real. So this way you can understand various different connection inside the chip fabrication process go through. So even before reaching the realistic process step, where in the above picture you can see the M2 is connecting, in the M1 etching step, the plasma induced charge, also known as the antenna phenomenon, happens, and it damages the gate oxide from the right hand side. This is a realistic action replay, means whatever we expect ideally and what happens in actual world. We are done with this infographics. Let's move on to the physics happening behind. Non-uniform density of plasma across the wafer plays an important role in antenna related damage. Remember, here we'll go deep into the physics happening in the antenna phenomenon. Such non-uniformity can come from non-uniformity in radio frequency, RF current flow, electron current flow, ion current flow. All these are related when a semiconductor process is going. In addition to this, the electron shading effect can contribute plasma charge. What is the electron shading? The plasma charging, that is metal, and discharging through oxide can severely degrade or destroy devices, especially metal oxide semiconductor, that is MOS gate dielectric. This particular problem is becoming more prominent in lower technology node with the thinner gate oxide. The gate oxide degradation occurs by the physics, that is the Fowler-Norden FN tunneling phenomena between the gate oxide and the silicon substrate. That means gate oxide, which is residing between the gate and the silicon substrate, goes through Fowler-Norden tunneling phenomena, and that starts the charge passing, creation of the percussion path, and finally when there is huge amount of charge flux is going through the oxide. In the continuous plasma exposure environment, the gate potential builds up, adjusts itself by the FN tunneling current. The flow of the tunneling current generates trap and interface states in the gate oxide, gradually degrading the oxide quality and integrity. At very high level of stress or prolonged exposure also ultimately lead to the breakdown of the oxide. In high aspect ratio spaces, isotropic electrons are hindered from reaching out the bottom of the space, whereas anisotropic and positively charged ions are not. This phenomenon is called the electron shading that I have just mentioned in the previous slide, which happens in the uniform plasma when topography exists on the wafer during the plasma exposure. Insulators such as photoresist or oxides are commonly used as masks when etching conductive films. The underlying conductor can acquire a positive charge by the electron shading mechanism. This way, I have pointed out all the physics that is happening behind the scene of the antenna breakdown in 2 consecutive slides. They are done here. Let's move on to the next. Antenna ratio. So this antenna ratio is a very important point, and you may get this ratio from your design rule manual, and it is very important for your antenna analysis. The magnitude of the accumulated charge depends on the ratio of the floating conducting region area to the gate area. This is called the antenna ratio and quoted in design rule manual. So the antenna ratio is equal to the total exposed antenna area divided by total gate oxide area. It can be equated with the current densities JFN, function of Vg, and Jp, that is function of Vg. Now what are these? Vg is the gate voltage on all the gate oxides connected to the particular wire segment, which is under the antenna effect consideration. The charging current density Jp is a function of the antenna voltage and the tunneling current density. JFN is a function of the gate voltage when the technology parameters are kept constant. The above equation shows the relationship between the antenna ratio and the current density. A higher antenna ratio means a larger Vg, and thus a larger JFN and more damage. This ratio very important with respect to the physics happening behind the antenna breakdown. So we're done with this particular slide. Let's move on to the next slide. Antenna issue mitigation. There are few ways to eliminate the antenna effect. Jumper insertion. This is creating a metal bridge, also known as jumper, near the gate of the MOS device. So that this is creating a metal bridge, also known as jumper, near the gate of a MOS device while fabrication. This jumper could take gate connections directly up to the top level metal through stacked gears. Here we are talking about the jumper creation in the BOL section. BOL section you can remember from the first slide. Consequently, the gate will not see any antenna due to the breakup of a long metal piece into stacked metal or via layers. The drawback of the use of stacked vias can lead to routing congestion and hence also the increase in die area. Stacked metal or vias may or may not lead to EM or IR reliability issues. Antenna issue mitigation. We continue here with few more points or few more ways of mitigating the antenna phenomenon. Gate protection diode. Here we connect each gate to reverse bias PN diodes. Using diode provides a discharge path directly to the substrate by contact to a diffusion area. If possible, these diodes are connected to gate with metal 1 so that prevention starts right with metal 1 fabrication. During normal operation, this reverse bias diode will not affect the functionality. However, the plasma-induced charge is discharged to the diodes, leaving the gate unaffected. Drawback is the usage of antenna diodes may increase the die area by 4 to 6%. So we are done with this slide. Let's move on to the next slide. Here we will be showing the antenna mitigation infographics to understand the mitigation process in a more visual manner. Here we will demonstrate the jumper creation. Here is our diffusion. Here is our poly and gate oxide combination of a MOS, and here we are reaching to M1, and then here we are breaking down the long M1 on the right hand side. This we have already shown in few slides back, you recall, and connect the M2 here while we connect the jumper here. So you can see the right hand side long metal piece of M1 is broken and taken through a jumper. Now this jumper connection is a simple connection shown. However, in reality this may spread very high in the BOL stack. Next, here we have the diffusion and we are showing here the diode method, and here is our poly and gate oxide combination, the MOS, that is MOS structure. Here we can think there is a MOSFET. And here we are reaching up to M1. Here we are using the M2, and you can see we are dropping the diode here. So this is the diode method. Antenna issue mitigation. Here we will proceed with two more mitigation techniques. Embedded protection diode. Add protection diodes on every input port of every standard cell. Here we are using a precautionary diode. These diodes are embedded and fixed, hence these consume unnecessary area. Diode insertion after PNR. Fixing only the wire with antenna violation, which will not waste routing resources. During wafer manufacturing, all the inserted diodes are floating or ground. One diode can be used to protect all input ports that are connected to the same output ports. So here we talk about the embedded protection diode method and diode insertion after PNR. We are done with this particular slide. Let's move on to the next slide. Here we will show the infographics of the discussed methods here. So here is our silicon substrate and it is our STI, source, drain, gate oxide, poly, source, drain, gate oxide, poly, and here we are reaching up to the metal 1, and then we are reaching up to the metal 2, and finally we are reaching up P, and the stack goes on in the BOL zone, and here we are reaching up to the M4. So this is a typical connection that is shown to you, and the right hand side MOS and the left hand side MOS belongs to two different standard cells. Now here what we do, as we have just discussed in the last slide, we keep embedded diodes per cell. That means for left hand cell there will be one diode and the right hand side there will be one diode. So here goes our diode. Here goes our diode. So this diode and this diode are the pre-existing diodes that will take care of the antenna issues, and these are included in the right hand side standard cell as well as in the left hand side standard cell. So this way pre-existing diodes, that means the diodes which take care of the antenna issue, are included during the standard cell. So here we are done with this particular infographics. Let's move on to the next slide. Here we'll go through another infographics. Here is our routing obstacles, and you can see that diode insertion prohibited area. So here we cannot do the insertion of the diode. And here we have routing obstacle. So you can see the layout here, and here also we have the routing obstacle. Now in this scenario, we have to include some antenna diode. What we will do? We'll proceed like this. Here you can see some changes if you compare the left hand side picture with the right hand side picture. And here are the diodes which are inserted PNL level. These are antenna diodes inserted during the PNL or after the PNL level, and this way we covered the two infographics of the discussed antenna mitigation method. So you're done with the particular slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe in case you have some dislikes. That as in words in the comment section down below, and bye for today.